Hi, this is Mrs. Nearing, and in this video, we are going to talk through some of the basics of ionic bonding. And one thing to keep in mind with ionic bonding is it typically occurs between metals and nonmetals. And the reason why this is because your metals have really low electronegativities. They're over here on this side of the periodic table. And we know that these elements over here on the left, they tend to have low effective nuclear charges. That gives them a weak grip on their electrons, so they end up with low electronegativity. And then the nonmetals over here on the upper right, they tend to have high effective nuclear charges. They've got a stronger grip on electrons, so they tend to have high electronegativity values. So what happens is when you put these two types of elements together, the metals are going to, or maybe it's better to think of it as the nonmetals are going to take electrons away from the metals. So if we were to summarize that, here's your metal, here's your nonmetal. Your nonmetal is going to take an electron away from your metal. As a result, you end up with a positive ion over there and a negative ion over there. And notice how they're not actually sharing any electrons. You just end up with a positive, negative ion. So what's holding them together is the resulting Coulombic attraction between these opposite charges. All right. So the metals will give up their electrons to the nonmetals. You end up with these positive and negative ions. And what they form is something called a crystal lattice. So this is a visual representing the crystal lattice formed when you make salt. So what we have is your sodium forms a cation, your chloride forms an anion, and there are no electrons being shared between them. What is holding them together is that positive-negative interaction. So it's a Coulombic interaction there. And key thing to keep in mind is there's no such thing as a molecule of salt. So when you are describing these substances, you want to be really careful with your language. The only things that form molecules are things with molecular covalent bonding. An example of a molecule, a common example would be like water. So when we draw water, we draw it like this, and the lines would represent shared electrons. That's how we represent molecules. Salt and other ionic compounds, they do not form molecules. So they do not share electrons. So sometimes I see people write salt like this, and that would be an incorrect representation because your sodium and your chlorine, there's no shared electrons between them. They are separate ions just being attracted together by this Coulombic attraction. And when you see this formula, NaCl, the formula for an ionic compound, we refer to this as a formula unit. So it is not a molecular formula because, again, it's not a molecule. So we call it a formula unit. And what that tells us is within the crystal lattice, there is one sodium ion per every one chloride ion. That's how we want to interpret those chemical formulas for ionic substances. Just tells you the ratio of ions in that crystal lattice. Another important thing to know about ionic bonds is that when you form an ionic bond, the number of electrons gained will equal the number of electrons lost. So, law of conservation of matter, these electrons are not just going to appear or disappear into thin air. So if someone's losing electrons, that's because someone else is taking them. So here's an example here where sodium and chlorine get together to form sodium chloride. Each sodium atom loses one electron to a chlorine atom, and then they form these ions. And notice how there's one electron gained, one electron lost. So this is a really key thing to keep in mind when you are forming these ionic bonds. So here's an example where we're showing this transfer of electrons using something called a Lewis symbol. So Lewis dot symbol would be where we use dots to represent valence electrons. So those are our electrons on the outer shell. So like if you look on your periodic table, you'd say, oh, look, magnesium has 2 valence electrons, so I'm going to give it 2 dots in this picture. And we know that metals tend to lose all their valence electrons. So magnesium has 2 valence electrons that it wants to lose. And if I'm considering how it bonds with fluorine, we know that each fluorine atom has 7 valence electrons, and there's space for one more. It's got one opening. So each magnesium will end up bonding with 2 fluorines because your magnesium is going to give 1 electron to each fluorine. So that's why when magnesium and fluorine bond, they form this compound, MgF2. So you need 2 fluorines for every 1 magnesium because magnesium has 2 electrons to give up. Okay. So with this in mind, you want to stop and in your notes, try and practice this for these 2 examples. So sodium and chlorine, sodium and oxygen. So if you haven't tried this yet, pause the video and try this on your own, and then you can restart it and check your work. All right, so I'm just going to start drawing this out. I'm assuming you've already given this a try. Sodium has 1 valence electron. Chlorine has 1, 2, 3, 4, 5, 6, 7. So when they bond, sodium is going to give an electron to chlorine. And I'll actually write out the result here. So sodium loses its valence electrons, and then chlorine then ends up with filling its valence shell. So notice how what I did not do is I do not want to show it like this, because writing it this way, this implies that they are sharing electrons, which they are not. Okay, they are transferring electrons. So we're talking about ionic bonding. In ionic bonding, the electrons are transferred from the metal to the non-metal. So there's no sharing happening. All right, let's look at sodium and oxygen. So sodium has 1 valence electron. Oxygen has 1, 2, 3, 4, 5, 6. So oxygen actually needs to gain 2 electrons. So we actually are going to then need 2 sodiums for every 1 oxygen. So what that looks like then is in the crystal lattice, you'll find 2 sodium ions for every 1 oxygen ion. And so the chemical formula here would be Na2O. The chemical formula here would be NaCl. That just tells you the ratio of ions in that resulting crystal lattice. As a result of the fact that electrons gained equals electrons lost, something else we will notice is that when you look at the ions that are formed, the total positive charge of your ions is going to equal the total negative charge. So basically the total charge of your cations will equal the charge of your anions. So like in the case of magnesium fluoride, magnesium forms a +2 ion. Each fluoride is -1. So you need 2 fluorides for every 1 magnesium. Over here, aluminum and oxygen, when they get together, aluminum will lose 3 electrons. Oxygen will gain 2. So in order to make that work out, you need 2 aluminums for every 3 oxygens. So notice how 2 aluminums, that adds up to a +6 charge, and this adds up to a -6 charge. So your positive and negative charges should always add up to 0, is what you should notice. And that's because your electrons gained will equal your electrons lost. So like if you think about this scenario, in order to make 2 aluminum ions, we had to lose 6 electrons. And to make 3 oxide ions, you need to gain 6 electrons. So that's what it all comes down to in ionic bonding, electrons being gained and lost, and those need to equal each other. And here is a shortcut you might remember seeing from first-year chemistry. If you're just trying to figure out what the chemical formula is of something and you want to make sure the charges add up to 0, electrons gained equals electrons lost, this is kind of like a shortcut trick to help you figure out the right ratio of your ions there. So yeah, this is basically just a trick to help you figure out what the right subscript should be. And that'll make it so your positive and negative charges add up to 0. Okay, now let's think about the energetics of ionic bonding. So we mentioned that when we have this ionic bond, you form a cation and you form an anion. And they're going to be held together by what we call that electrostatic attraction, or sometimes we refer to it as, Coulombic attraction, and between these positive and negative ions. And we know that whenever we have this positive negative attraction, we can think about the strength of that attraction by considering Coulombs Law. And notice how there's 2 versions of Coulombs Law. There's a version, this version describes like the attractive force between the ions. This one describes the potential energy. But notice how in both cases, it's charge divided by distance. So I just want to point that out. If you've done some physics calculations in the past, you might see these two different versions of this equation. But in both cases, as the charge goes up, they become more attracted. As the distance goes up, they become less attracted. And so we've already talked about Coulombs law in the context of the structure of atoms and thinking about the attraction between an electron and the nucleus. When we're thinking about ionic compounds, we're going to use Coulombs law to describe the attraction between the two ions. So in this context, and we're thinking about, how the force is the proportional to charge divided by distance. When we're thinking about ionic compounds, the charge is going to represent the charge of the ions involved. So they could be +1, +2, +3, -2. So charge of the ions. And then the distance is going to have to do with the radius of the ions. So as the radius of the ions increase, then you can kind of think of it as, like, let's imagine you have two small ions. You can think of them as being like relatively close together. If you have these ions with a really big radius, then you can think of it as like these are further apart. And so the further apart they will be, the less attracted they will be. So let's look at some examples of this. Some of the variables are the size of the ions and the charge of the ions. So ion charge is on the top. And then ion radius is that basically that distance value on the bottom. So notice that, like, if you look within these first few compounds, these are all lithium compounds. They all have the same ion charges. They're all like +1, -1 ion combinations. But as you notice, as you go down from fluorine to chlorine to iodine, if you look on a periodic table, they're all in the same column. And as we know, as we go down a column, the radius is going to increase. So as a result, we can see that the lattice energy is going to decrease. And I think I skipped over actually explaining what lattice energy is. Let me go back a slide. So the lattice energy is basically describing the attraction between the ions. This is the technical definition. It's the energy released when the ions combine to form a crystal lattice. Basically, you think of the lattice energy as the attractive force between the two ions. So if the ions are more attracted to each other, they've got a higher lattice energy. As a result, we'll observe them having things with a larger lattice energy. The ions are more attracted to each other. That means it takes more energy to separate those ions apart from each other. As a result, we'll notice, like, when you look at their physical properties, they'll have a higher melting point, higher boiling point, things like that. All right, so now let's go back to this one. Okay, so we'll see that as the radius of the ions increases, when the ion charge stays the same, the lattice energy goes down. So what we're seeing here is as the distance, increases, the, attractive force between them is decreasing, right? This fits with what we know already about Coulombs law. We can see the same thing happening among these ions. These are all examples of +1, -1 ion combinations, but with increasing ionic radii using our periodic trends. Iodine has a much bigger radius than fluorine. As a result, we can see that the lattice energy within this group is decreasing. Okay, but if we let's compare to these ions, magnesium and oxygen. Magnesium is a +2 ion, oxygen is a -2 ion. Notice how if you compare any of these ones with any of these ones over here, on the left, these are all +1, -1 ions, and these ones are all +2, -2 ion combinations. Notice how these have much larger lattice energies. So that's evidence that as the charge increases, the lattice energy, so that attraction between those ions, is also going to increase. We see they're significantly bigger, right? So it's almost like 3 to 4 times as big. And then still within these, as the radius increases, the lattice energy decreases. So those are the trends we want to observe here, and we want to use these patterns right here to make some predictions about who would have relatively larger, smaller lattice energies. So here's some examples here. So we want to predict who would have a higher melting point. So this is where we want to stop and point out things that would have a larger lattice energy are going to be held together more tightly. So they end up having higher melting points. So when we're asking who has a higher melting point, we're basically just asking who has the higher lattice energy in these pairings. So what I want you to do is I want you to pause the video and make predictions first, and then restart it and check your work. All right. So I'm assuming you've already paused and made some predictions. So let's take a look here. So sodium chloride, let's look at the ion charges first. So sodium chloride, that's +1, -1. Magnesium oxide, that's a +2. Those are +2 and -2 ions. So we know that as the charge increases, they're going to be more attracted. So I'm assuming MgO has a higher lattice energy and a higher melting point than sodium chloride. Let's look at the next pairing. So lithium's +1, fluoride's -1. Sodium's +1, bromide's -1. So the charges are the same. So now let's look at the other variable, which is distance. So let's compare on a periodic table. If I look on a periodic table, I can see that bromine has a much larger radius than fluorine. Don't believe me, check your periodic table. Same thing with sodium. Sodium also has a larger radius than lithium. And I'm just applying my periodic trends that we talked about. So since these have a larger distance, they're going to have a weaker attraction. So lithium fluoride would have the higher melting point. Because remember, again, if we look at what our relationship here is that the attractive force, okay, which is the lattice energy is a way to think of the attractive force between the ions, is going to be directly proportional to the ion charge and inversely proportional to the ion radius. So the larger the charge, the more attracted they'll be. The larger the radius, the less attracted they'll be. Let's look at one last one. Let's look at our ion charges first. And I think always look at those first because that's the easier one to think about. Okay, so if you look at your ion charges, then we can see that this is a +2 and a -1 ion, and this one's a +2 and a -2 ion. So we have larger ion charges, so they're going to be more attracted. And you might be wondering, like, well, but this one has 2 chlorines, so doesn't that count? Should I add them up? But no, you just want to look at the individual attraction between ions. And it might help to look at what this would look like in terms of a crystal lattice. So here's what the MgCl2 would look like. Here's what the strontium oxide would look like. When we think about the lattice energy, the attractive force between the ions, we're just looking at 2 individual ions and asking how attracted are they. So these 2 ions are going to be more attracted than these 2 ions because we see larger charges over here on the right than over here. So the strontium and magnesium are both +2, but over here the oxygen's -2 is more attracted than the -1 chlorine. So those are 2 variables you want to look at when you're predicting relative lattice energies. All right, thanks for watching.